In this video, we are going to take a look at sequences. Now that you've looked just at general sequences, we're going to look at two specific types that follow a pattern, and we can use an equation to help find other terms in. And they're arithmetic and geometric sequences. So we'll start with an arithmetic sequence. An arithmetic sequence is just a sequence in which each term differs from the previous one by the same fixed number. The important word here is differs. So to get from one number to the next, I'm going to be either adding or subtracting. So an example of this, or two examples of this, are the following sequences. So 2, 5, 8, 11, 14, etc. That's arithmetic, because when I take my second one and subtract my first, I get 3, which is the same thing as when I take my third and subtract my second, I also get 3. 11 minus 8, I get 3. And then 14 minus 11, I get 3. So there's that common difference between there, where that common difference therefore is 3. This next one as well is, again, it's adding or subtracting. So in this case, when I'm subtracting 4 each time, I keep getting my next number. So after 19, I can subtract 4, and I know my next term is 15, etc. So these are just specific examples of arithmetic sequences. Now what we can do is we can write equations for arithmetic sequences. One of the things that you'll see in different textbooks is they use different looking formulas. They are all doing the same thing though. So the formula that we're going to use, and you're going to see here, is u sub n equals. Now it could say a sub n, it could say t of n, it could say t sub n. All of these notations are just different ways to state this. So u sub n equals u sub 1 plus n minus 1 times d. So this would be a formula you have to memorize. And we're going to end up finding the equation for that first sequence we had before, 2, 5, 8, 11, 14, etc. Some of you might look at this and go, okay, I can find that equation easier. You're absolutely right. I'm going to show you two different ways to come up with the equation. One of them is using this generated formula that works every single time, and then the other one is based on previous knowledge and previous skills that you have. What each of these terms mean is u sub n means any specific value, u sub 1 means your first term, n is whatever term in the sequence we're looking for, and d is that common difference. So in the example that we started with, we had 2, 5, 8, 11, and 14. And that keeps going forever. So if I want to write my equation for this, I can go through u sub n equals u sub 1, my first term, which is 2, plus n minus 1, which is going to help me find any term in my sequence, times my common difference. So each time this is adding 3. So times 3. Be careful if it's a subtraction, or if it's subtracting 3, make sure you put parentheses around it because it's multiplied by it, it's not subtracting it. Now, I look at this equation. This is not very simplified. I can go through and expand. So when I do that, I get u sub n equals 2 plus 3n minus 3. Combine those like terms. U sub n equals 3n minus 1. This is a simplified equation, and that's the equation that you would be using from here on out to find different things. So this is a linear equation. Y equals mx plus b. If you think about y equals mx plus b, m is your slope. That's what you're constantly changing by. As it increases by 1, as your n value increases by 1, your u sub n value increases by 3. And then, somehow, though, I have to find this negative 1. Now, if it's in slope-intercept form, that's your y-intercept. So if I go backwards, I need to find my 0 term. There is no 0 term in sequences. However, if I go back and were to find that quote-unquote 0 term, I'd have to subtract 3, which gives me negative 1. So whichever way you want to come up with your equation, you are perfectly acceptable to do this with. You can memorize this top formula and plug in your numbers accordingly, which takes you here. Or think about the fact that it's a linear equation. Find your y-intercept, go backwards. You have your slope, which automatically gives it to you there. So you have a couple of options for that. So at this point, pause the video and go and work on the worksheet for arithmetic sequences. So now moving on to geometric sequences. For our geometric sequence, a geometric sequence is a sequence in which each term can be obtained from the previous one by multiplying by the non-zero constant. Keyword here, multiplying. So if we're multiplying by that non-zero constant, I can keep coming up with each of my terms. So an example of this would be 2, 10, 50, 250, etc. That's a geometric sequence because 2, first term, times 5 gives me 10, and 10 times 5 gives me 50, and 50 times 5 gives me 250, etc. So I need to figure out what that multiplier is. So algebraically, the easiest way to find your multiplier is to take your second term and divide it by my first term. So up here, it'd be 10 divided by 2, 50 divided by 10, etc. To figure out what that constant multiplier is. Algebraically, if you want to do that, all you're doing is finding your u sub n plus 1 and dividing it by your u sub n term. Because if, for instance, 2 is my u sub n term, u sub n plus 1 means my next term, which is where the 10 is. That's why it's 10 divided by 2. So that's going to give you your r value, which is your multiplier, your common ratio. The formula that you will use for this one, or can use for this one, is u sub n equals u sub 1 times r to the n minus 1. Again, a formula that you can go through and memorize. With this formula, if you prefer not to memorize this one, there is another option that you can do with this. If you notice, this is an exponential function. So we can use our equation, remember from exponentials, y equals a times b to the x, where b is your multiplier, a is your y-intercept. So if you know your multiplier and can go backwards and find your y-intercept, again, keeping in mind that we don't have our zero term necessarily with sequences, but you can always go backwards and find it. You can set up that one, or this one will consistently work as well. It's your choice which one you're comfortable with. If you struggle trying to write the equation, if you like trying to use the exponential but you're struggling with it, you may need to come back here and use this generic one for u sub n. Okay. So we will make an equation, therefore, for the first one, 2, 10, 50, 250, etc. So we already talked about, we know that our multiplier is 5. That's my r value. So r is 5. So in my equation, u sub n equals u sub 1 times r to the n minus 1. Since I know my r value right away, I can put that multiplier in there. And I know u sub 1, which is my first term, is 2. Now this one's a little bit quicker than your arithmetic sequence because for this one you don't have to go through and simplify. I'm done at this point. Option B is if you want to write it as if it was an exponential equation. We still use the u sub n. I know I had written y equals, but we still use u sub n so that we know we're working with sequences so that our exponents can only be integer values. Those n values can only be integers. So I need to find my, as it shows here, my y-intercept and my multiplier. Well, I already know my multiplier. My multiplier was 5. This time it's only to the n. See, that was to the x, so this is x, and this is u flip it. So I already had my multiplier. Now I just have to find my y-intercept, which means I have to go backwards. Going forwards, I multiply by 5. Therefore, going backwards, I have to undo the multiplication, so I'm going to divide by 5. So 2 divided by 5 is 2/5. Both of these are completely acceptable equations for an exponential. For a geometric sequence, which are exponential functions. So at this point, work on your geometric worksheet to practice the different types of problems you're going to see.